This section of the video is to show you how you can use Desmos to check an RMS value of a voltage. Okay, so in this one it's set up as 110 volts. I have to turn off some of these things here. Okay, so here we've got our sinusoidal wave. Okay, sine wave starts at 0, goes up to a peak at pi over 2 radians, returns to 0 at pi radians. Okay, and finishes its cycle at 2 pi radians. Okay, so if we were to try and measure the voltage of this wave, as we pass along the wave, the voltage would increase. So there is at 89 volts. Okay, down here it's 33 volts. So it would depend on where in the cycle you measured it. So we need to be able to take a more reliable measurement, and that's where RMS comes in, root mean square. So this is our function here, V sine theta, and the Desmos chart has got a slider on it so you can change the voltage. So if I drag that down to say 12 volts, then it changes the shape of the wave. Okay, so I'm going to go for 110. Okay, so you've also got the current goes in, or the voltage goes negative at some points. So what we want to do is to take to square it, okay, and then take the square root of it. So whenever we square it and take the square root, these troughs are all above the positive axis or the x-axis. Okay, so instead of having alternating, we've got these humps, and by taking the root mean square, which is find it here. Okay, we can find the mean of those humps as a measurement of the voltage. Okay. Now, my own students, whenever you're doing your assignment, you're going to have to calculate and prove the RMS figure. This is the formula for it. Okay, so it's the square root of 1 over b minus a times the integral from b to a of the function squared with respect to the angle. Okay, so I'm going to put this link in the comment section of the video so you can actually come in here and play around with this. If you want to check your answer, you can drag this, say you answer your voltage and your question was 60 volts, then you can look and see the RMS figure should be 42.4 volts. Okay, that should give you an indication of whether your calculation is correct or not. Okay, so it's quite a handy wee tool, but obviously this isn't sufficient to answer the question. You have to show that you're able to use integration to find the RMS figure, basically prove it. Okay, but again, the link is there and you can play around with this video anytime you want. Try to play around with this Desmos graphing chart. Okay, in the formula for the RMS, we've got B and A. So just need to explain what those are. Those are the limits along the graph here. So at the minute, sliders are set to start off at 0. So A can be changed to be a different one, different value of angle. But we're setting it at 0, and at the minute B is set up to be 2 pi radians, which is a full cycle. So if you want to calculate it over half a cycle, which should give the same answer, you just drag that down to cover half the cycle, okay, and it's shaded there. So that's how you use the sliders for the limits on the equation. So A would be 0 and B would be pi in this case. Okay, I just realized that the question is about current, so I changed the Desmos graph to have current instead of voltage, but it really doesn't matter. The same theory applies. So the link will be in the video comments. Okay.
Okay, so we're going to plot a current. Okay, so something like this, sine wave. Okay, and angle. And here we have pi and 2 pi and 0. Okay, so we want to work out the RMS figure over half a cycle, and therefore we will get a steady state figure for the current. So for this example, I'm going to work out current of 110 sine omega t. Okay, now omega is the angular velocity and t is time. So if we multiply those two together, we get theta, the angle turned through. So another way of writing this is 110 sine theta. Okay, the formula for RMS is equal to the square root of 1 over b minus a integrated from a to b of the the current squared with respect to the angle. Okay. Now what that does, the root mean squared means that this bit that's underneath, because it's square, because we square it and then take the square root, it ends up being on top. So we don't have any negative current, and therefore it's easier to work out the steady state value. So that's why we square it and we take the square root. Okay, so for half a cycle, a equals 0 and b equals pi, because we're going up to this point here. So we insert those values in. So the IRMS square root of 1 over pi minus 0. Integrate from 0 to pi of 110 sine theta squared d theta. Okay, so IRMS is equal to the square root of 1 over pi integrating from 0 to pi. So everything inside this bracket gets squared. So we square the 110, and that comes out at 12,100. And we get sine squared theta d theta. Now this bit here, we have to do something with this because we can't integrate it when it's squared. So we have to express it as a different function. Okay, so by using trigonometry, we can express sine squared of an angle as another trig function that doesn't involve a squared value, and therefore we can integrate it. So that's the next step. The next step is to change the form of sine squared theta, as it's not possible to integrate this. Okay, so from reference books, we have these half angle formulas. Right? You don't need to remember them off by heart, but you just need to be able to use the highlighted one there. Okay, so here's cos squared, can be expressed as cos 2 of the angle. Sine squared is 1 minus cos 2 of the angle over 2. Okay, so we're going to rewrite that. Sine squared theta equals, instead of putting the half on the bottom, I'm going to put it outside brackets. So half times 1 minus cos 2 theta. Okay, and we're going to insert this part here in here instead of sine squared theta. Okay, now before I do that, I can move any constants out of this integration because they're not dependent on theta. So I can rewrite this. Okay, square root of 1 over pi integrate. Sorry, move the 12,100 outside the integration over the pi from 0 to pi sine squared theta d theta. Okay, now I can insert this value. So RMS or 12,100 over pi, integrate it from 0 to pi, 1 minus cos 2 theta, don't forget the half, d theta. Okay, so again, the half can be moved outside. So 12,100 over 2 pi, that's our half, so it's on the bottom, 2 is on the bottom of the fraction, from 0 to pi, 1 minus cos 2 theta d theta. Okay, and the next step is to integrate this section here. So we need to look at how you integrate trigonometric functions, which we did in first year. Okay, so just a quick recap of integrating trig functions. Okay, we have cases where we have cos kx, which k is constant, or sine kx, then these are the integral values for those functions. Okay, so for example, sine kx, I know we're doing cos, but if we look at sine, if we have sine kx, we get minus 1 over k cos kx plus c. So in example 1, the answer to that would be minus 1 over 3 cos 3 theta plus a constant. Okay, and that's because integration is the opposite of differentiation. If we differentiate this function, we will get this one, and the constant will disappear. Now, when we do it between limits, we don't need that constant, so it'll be slightly different once we do our calculation. Example 2, this is cos 5 theta. So in this case, cos kx integrates to give 1 over k sine kx plus c. So in this case, it'll be 1 over 5 sine 5 theta plus c. Okay, those are two separate answers. So in our RMS case, we're going to integrate 1 minus cos 2 theta. Okay, so that will be equal to, the 1 integrates to become theta. Okay, if we differentiate theta with respect to theta, because there's a 1 in front of this, it would become 1. So when we integrate 1, we get theta. And cos, so we get minus, and then we integrate cos 2 theta. So cos kx is equal to 1 over k sine kx, or k theta in this case. So there's a 2 is our k, so it's 1 over 2 sine 2 theta. Okay, and then we would have a plus C if we're just working it out. Okay, whenever we go to do our RMS calculation, we have two limits here, so we get rid of this constant in the final calculation. Okay, so now we're ready to do our final calculation. So from a previous page, I put the IRMS as the square root of 12,100 over 2 pi, integrated from 0 to pi upon 1 minus cos 2 theta with respect to theta. Okay, so we're going to put this part here in as the integral of this part here. Okay, so IRMS is equal to the square root of our constant, open square brackets, and we put this figure, or these, in here. So theta minus 1 over 2 sine 2 theta from 0 to pi. Okay, so now we will insert the pi figures first into this, and then we will take away another bracket with the 0 angle inserted for theta. Okay, I'm just going to leave it a little bit more room here. It's going to be longer. Okay, our constant figures are the same. Okay, so we insert pi first of all. So we have pi is theta is equal to pi minus 1/2 sine 2 times theta, which is pi, so it's sine 2 theta. Okay, minus theta is equal to 0. Take away 1/2 sine 2 times 0. Okay. So if we quickly look at the sine graph, we've got 0, pi, 2 pi. You can see here that at an angle of 0, this is theta. At an angle of 0, our current will be 0. Okay, and 0 is 0. So this whole half part here tends towards 0. Also at 2 pi, when you do it, put it in your calculator, you'll find it's 0, but from the graph, it's also can be shown to be 0. So this part goes to 0 as well. Okay, so we're left with the IRMS equals square root times pi. Okay, the 2 pi's cancel out. So we're left with 12,100 over 2. And if we work that out in your calculator, 77.78 amps